Assalamualaikum warahmatullahi wabarakatuh, and good afternoon to everyone. I welcome every of my students and also the student from the section 1 to join in for the lecture online interaction for abstract algebra. In order for you to understand this chapter, you must have a good understanding on how to do proving. Please look at this video entitled Extra. I put the extra. Mana? This one, extra logic and proof techniques. Please look at the YouTube video and listen carefully because the techniques of proving the fundamentals should be mastered first before you can enter this chapter. Abstract algebra is a field of pure mathematics that focus on the structure of algebra. There are two subfields. The first one is abstract algebra. The second one is modern algebra. Modern algebra is the one that you already learned during your school. For example, what Al-Khwarizmi state that how to represent variables, how to solve simultaneous equation, how to solve quadratic equation, and that so on and so forth is known as modern algebra. Abstract algebra is the field that is being introduced by Evarita Galois in the year of 1800, that it studied the characteristic or the nature of how numbers should operate. This one is so abstract. We study the fundamentals of the fundamentals. Interestingly, what Evarita Galois already teach us during 200 years ago, is not known. The benefit is unknown until the modern 20th century. People realize that it is actually useful. In order for you to embrace this chapter, you must try to think as abstract as possible. It means as fundamental as possible. It includes why. I start with my writing right now. For example, why A plus B is equal to B plus A. For example, this A and B, you let be any integer. You let it be any integer. You know that A plus B equals to B plus A. You know that. You already know that. Right now, we are studying not only for A plus B equals to B plus A. You can also ask this question. Is A minus B equals to B minus A for every integer? For the first one, I can refutely say that, yes, confirm. It's a statement, it's a properties, and it's a well-known properties that A plus B equals to B plus A. This is correct. It's true for every possible integer. For the first one, but the second one, is A minus B equals to B minus A for every integer? The question, I just put some counter example. I take 1 minus 2 equals to negative 1. 2 minus 1 equals to 1. Negative 1 is not equal to 1. Therefore, 1 minus 2 is not equal to 2 minus 1. For subtraction is not commutative. This property, characteristic ini, is also known as commutative. Addition of integer is commutative. Subtraction of integer is not. This is one of the fundamental characteristics that you will learn in this chapter. Okay, today we will start with the introduction of a group, which is one of the abstract, the algebraic structure. We start first with a binary operation. You learned ordered pairs, Cartesian product, in chapter 2, where you take one element from A, set A, you Cartesian product with element from set B becomes an ordered pair. This one, and also you learn binary relation in the relation subtopic. This one is binary operation. It's a function of set, still in the form can be formed from the Cartesian product here, A times A. It will produce some output kat kanan ni, on the right. Just now I show to you A plus B. This is one element, this is one element, the first element and the second element, and this is the plus addition there is the binary operation. Okay, my example is that 1 plus 2 just now, you take one element from integer 1, you take one element from integer which is 2, and you binary operation them with addition, becomes 3. This is one of the example. Why the name binary? Because at one time it involves only 2 elements. And let me put you into the perspective of 3 elements right now. 1 plus 2 plus 3. Some of you might argue is that this is tertiary operation. Bear in mind is that in many calculation, in any basic arithmetic calculation, even for the computer themselves, they usually can add 2 elements at one time. Becomes 3 plus 3, and it becomes 6. You not always add up 3 elements at the same time. As you can observe that, you can also add up 2 elements at the back first. Becomes 1 plus 5 is also 6. This characteristic is also known as associative. Okay? Hence, binary operation, to sum up this subsection, is that binary operation can be defined as A star B. Again, A from the first set, this is from the second set, and this is the binary operation. This binary operation can be many operations. For example, just now we do plus. It can also be minus. It can also be multiply, division. Not only that, it can also be in terms of union, intersection, mutually exclusive, and various more operation can be represented in the binary form. Any question before I proceed? Student from section 1 also can ask a question, by the way, because student from section 2 ni dia malu sikit, dia pemalu sikit. Banyak kot. So section 1 pun I assume that you are not that shy. Because Miss Anis dia bukannya pemalu pun. Ada. Sorry Anis. Okay. Do you have any question before I proceed? No, So, korang pun pemalu juga section 1? No lah, I assume that you understand. So, it's a good thing for me. You don't ask question because you understand. Not because you run away from this. You're on the video lecture, you're on the Google Meet and then you go somewhere. Jangan buat macam tu. Okay. Now, we focus on the group. Okay, we really will go through a very deep mathematics here. In the slide, you show there is a 3 properties, but it's better for you to distinguish it to become 4. So you can understand the meaning of closed. If you read the definition on the slide, group is defined as a G if closed under operation and satisfy 3 by the distinguished. Kami tutup balik. Okay. Close, so that you understand what is the definition of close. Okay, the meaning of closure is that you take a set G, 2 elements from set G. G is closed if for every 2 elements from G, the binary operation between them will produce another new element, let's say C. This C must also be in the same set of G. That's the meaning. For every 2 elements from G, the binary operation of those 2 elements will produce one element which belongs to the same G. Okay, that is the first one. The example I will show you later. Number 2, it must be associative. This one I already showed to you previously, just now. For every 3 elements in the G, it exhibits this characteristic. You do the first bracket, is similar with when you do the next 2 brackets. This is the meaning of the characteristic of associative. The third one, identity. The keyword there is identity. It means for every element in G, there is some identity which belongs to the same G, such that this happens. A binary operation with E will produce commutatively E binary operation of A. You get back A itself, hence the name identity. At this point, most of you will already know the concept. You already heard identity. Identity ke mana kita dengar? There is identity of matrix. Correct? Kenapa nama dia identity? Why the name is identity? It will be explained later in our next lecture, perhaps. Identity means that for every element, your binary operation with that identity will produce itself back. And if you have identity, you can have inverse. You also have inverse matrices. Inverse matrix. Okay, contoh, example. Okay, no, definition first. Inverse means that for every element in the G, there exists the inverse. Inverse of A, say I put the notation, the power of -1. It means inverse. In the same G, such that this happen, A binary operation with the inverse is equivalent commutatively with A in binary operation A, you get E. Identity and inverse is closely related. If you have identity, you might have inverse. Okay? Because it depends on ED here. Okay. Right now, at this point, let me directly tell you that if you satisfy all these 4, you already have group. But if you have commutative, while we are at this point, I directly tell you about abelian group, because you just add up one more characteristic. Commutative means for every 2 elements in the same G, this happen. A binary operation B sama dengan equal to B binary operation with A. That's all. A group satisfy 4, but abelian group, it satisfy 5. Okay, got it? Okay, this is the fundamental. Okay, sekejap. Saya nak padam ni je. Okay. In the later chapter, you will go through semi-group and monoid here, 5.3 group 5.2, abelian, semi-group and monoid. Okay, I try to combine these three at the same time. Okay, listen carefully. There are 4 structures here. The first one, if any G is closed and associative, it satisfies only 2, we call it semi-group or semi-group. But if it satisfies closed, associative, and also identity, is satisfied 3, we call it monoid. So the smallest abstract algebraic structure that you learn is semi-group, monoid, a little bit larger. Then you have group. Next, you have abelian group. I repeat, if any G satisfy closed and associative, then we call it a semi-group. Semi-group only satisfy 2. You add up one more, we call it monoid, if it satisfy identity as well, if there exists identity. If you add up inverse, then you have verified that the G is a group. And if you verify one more commutative, then it is also known as abelian group. The properties, the definition for each of the characteristic, please memorize it by heart. Ni hilang satu je. E, okay. Ni apa ni? Terpadam juga. Buruknya. Sekejap. Okay. Bukan 9 no, not 9 lah, A. Okay. Before I proceed, for the examples, because Dr. Sham's slide here, the example is not that friendly, I will use a simpler example first. Okay, tak ada soalan ke ni? Sir, voice not clear. I don't know. Yu Wei Chiang. Yang lain clear tak suara saya? Because one of your friend here say it's not clear. Is it clear, my voice, or not clear?
Just now, not
Kinda
clear,
distorted.
Now clear.
Now clear. Maybe line kot, Maybe line, Okay. Okay, saya buat sambung balik ya. Kalau ada problem boleh cakap. Boleh. Tapi kalau if it's urgent, don't use little robotic sound. Oh, sebab saya bukannya manusia. Saya robot. Suara saya memang robot kot. Saya tak tahulah. That's why I hate online learning. Not you guys lah. Saya lebih benci. Suara saya sedap lagi. Tapi dia jadi robot. Okay, sambung balik. Okay. Okay, please remember this slide. The definition in terms of G, A, B, C kat sana tu, please master that. Now let's start with the actual example. Okay, I will purposely open the definition on the left so that you can be clear that. Okay, now how to read a group. For example, you get this question. Prove. Suppose this is given to you. I take the simplest one. You must know how to read this one first. This is the element. In terms of generally, we say this is G. Set. Okay. This one is the binary operation part. The left one is the set. or domain. The right one, we call it the binary operation. In English, this representation of symbol is just a addition of integers. This is what it means. Prove that the addition of integers is a group. Okay. We start with the group first, because that is the basic one. Group satisfy 4. So we start with the closed. And based on the previous definition, general definition, it says that for every 2 elements in the G, okay, kali ni, this time I don't want to say G anymore. I want to directly go into the actual question of the domain of the question. For every integer, okay, it will, A plus B will produce something, C. The question is C is in integer. Let me ask you this. You take one integer, you plus integer. The outcome, will it be integer as well? This one, you kena fikir. Integer plus integer. Will it be another integer as well? This is a basic property for every, you must mention not in terms of example. If my student answered only this, yes, it's close. This is the wrong one. Not wrong lah, more like not enough. If you say yes, exactly, it's close. Because 1 plus 2, 1 is integer, 2 is integer, 3 is an integer. If you answer like this, if you recall from the video that I asked you to look just now, then it will be wrong, because for every quantifier, you cannot put one example. This is not true, not enough. It must be in the general term, like the top one. So to answer this question, actually the answer, is it close? This is the actual answer that can be accepted. It is close. Because for every 2 integers, A plus B, C is always an integer. This is the statement already, the proof already. It is close because it is a well-known fact that A plus B will produce an integer. That's all that you can answer. Cukup. Seems weird, some of you guys. Ini jawapan ke? Actually, this is the mathematical statement that is true, by the way. Yes, it is an answer. Now let's look for associative. Okay, please refer the lab here. Tengok saya tak tulis. Is it associative? Right now, you know, just now from the previous example at the earlier part of this online interactive lecture, 1 plus 2 plus 3 is equal to 1 plus 2 plus 3, bracket, bracket. Actually, this Z plus is associative. Because you know, fundamentally, for every 3 integers, A plus B plus C is equal to A plus B plus C. Enough. This will be your answer. It's a well-known fact for plus. If I want to do this slightly slower, I add one more step. I also can do like this. A plus B plus C, open the bracket, becomes like this. And eventually still the same like this. Therefore, right now, the addition of integer is a semi-group already because I already showed that it is closed and associative. But I cannot confirm it is a group yet. Okay? Right now, it is closed, it is associative, addition of integer is a semi-group. Now, we go to the third one, identity. Okay, identity, Identity is special because it involves for every element in the G, there exists identity. If you look at the YouTube video that I mentioned just now, video of me, of course, that one, existential, you must mention, you must mention what is the identity. As an analogy, let me tell you this. There exists a boy listening to my lecture right now. There exists, Kalau exists, I must mention who is the boy. The boy is Mufamin, for example. It means that there exists a boy in my video lecture right now. Proof tu tak cukup. The proof is not complete if I not say who is the boy. Jadi kalau untuk existential quantifier, you must mention what is E. Let me picture you this. A plus E. Okay, contoh dulu, contoh. I take A equals to 1. What is the identity such that this happened? Can someone tell me this? What is the value of E? Jawab sekarang. The E is 0. Azizi, 0. Okay. Yes, the E is 0. Correct. This is very true. 1 plus 0 equals to 0 plus 1. You get back 1. And if you look at the left here, this identity, the unique identity, must be applicable for every element. Okay, now we look like this. For every integer, is there exists A plus E equals to E plus A, you get back A. Regardless lah A tu apa, A tu 1 ke, A tu 2 ke, A tu 3, 3, 4, 5. E tu kena sama. The E must be the same. And based on your answer just now, you say that the E is 0 for 1. But actually, the E also for 0 is applicable for every integer. Right now, what I can conclude is that there exists identity for Z under addition. This time, E is 0. This is the answer that I want to look for my student. If you just say identity exists, but you don't tell me what is the value of E, your answer is not sufficient. You must mention what is the E. You must mention who is the boy. The boy is 0. And let me mention you the tips. The addition, if you involve binary operation of addition, the identity is always 0. For multiplication is always 1. Okay. Now we look. Right now we just proved that the addition of integer is a monoid because it satisfies closure, associative, identity. It is a monoid right now. Now we look at the last one, inverse. Okay. Example first, not the actual answer, not the actual complete answer, but it's a good way of you to develop the cognitive thinking towards that. This time I take A equals to 2. Okay, 2. Does exist the 2 inverse such that this happens? 2 plus 2 inverse equals to 2 inverse plus 2, you get back the identity. Identity you get from the top. It must be equals to 0. What will be the inverse of 2? Jawab. What is 2 inverse this time? Thank you. Thank you, Dia Rahman Daniel. This is very clear that 2 plus negative 2 is equal to negative 2 plus 2, you get back 0. The 2 inverse, the inverse of 2 is actually negative 2. You are correct, Dia. Right now, this is not only for A equals to 2. The definition states that G is has inverse is that for every A in Z, there exists a unique inverse in the same Z, such that this happen. Binary operation. A plus A inverse equals to A inverse plus A equals to 0. This time is also involved existential. You need to tell me what is the inverse for every A. Just now, the inverse of 2 is negative 2. What is the inverse of A? And the answer is that the inverse of A is negative A. This is the answer that I sought from my students, especially if it involves infinite set like integer. Right now, number 1, number 2, number 3, number 4 has been satisfied, has been clarified. All the characteristic, it shows that right now I already proved to you that the addition of integer is a group setter. Now we look back at my working just now. Okay, this is a standard question, and every year I will ask not this question. I will ask, determine whether this is a group or not by checking all the properties. Okay, let me add this by checking all properties. Soalan spot lah ni, mesti ada. But the thing that can change is the set G and also the binary operation. How many marks here? At least 8 marks because of the length of the solution. Any question before I want to take a break? Okay? Take a break for 2 minutes. We will resume 1:50. Okay, 150 right now. We proceed with a more simpler example. Not simple. I show you the one that is not a group. Okay, like this. I'm worried that it will be the question of your assignment. Saya dah ingat soal assignment. Okay, tak apa. Let's show like this. Determine. Okay, this is the division of integer. Is a group or not? Okay. Or let me try to abelian terus lah. Abelian commutative. Okay, we start with closed. Is it closed? The division of integer, is it closed? If it is closed, then for every two integers, A divide B will produce C. C is an integer. Question. Is this statement true or not? If not true, provide me counter example. If it is true, then you can leave it as it is. Right now, is it true or false? Boleh jawab tak? Can someone answer me? If you can answer this, then you are thinking like a mathematician. You can be a mathematician like me. Ya, ada orang jawab. False, kenapa? Wah, laju jawab. Yes, that's very good. Chi Kintan, give me the actual counter example already. If you answer, it's not close. Or false, it's not closed. Not close, baru satu markah. Just one mark. But the reason you add one more mark, I use the reason provided by Chi Kintan and Yong Jian Lee. Beza sikit jawapan dia tapi boleh terima. Saya pakai Chi Kintan. Chi Kintan states that if A equals to 2, B equals to 3. 2 divided by 3, you get 2 over 3, which is not an integer. Very good. This is the answer that I sought for. Betul. Seek for. Very good. It's not close. Let's look for the associative. If it is indeed associative, then A divide B, you do the first part, then you do this one. Is it the same if you do the back part? Again, is it associative? I give you the answer. That is not associative. Associative. But if it is a counter example, you need to tell me your proof. I can simply say like this. If A equals to 1, B equals to 2, C equals to 3. You do on the left one first. There is an equality there, so you can do left hand side first. 1 divided by 2 divided by 3. Let's say I do the first one, it will be 1 over 2 divided by 3 becomes 1 over 2 times 1 over 3 becomes 1 over 6. It's not an integer, I know. But right now, I want to prove that it is not associative by this way. 1 divided by 2 over 3. 1 times 3 over 2 becomes 3 over 2. It's very clear here, 1 over 6 is not the same with 3 over 2. Therefore, 1 divided by 2 divided by 3, is not equal to this. This is the answer and the proof that I look for. Nampak? This is important. That's why proving, the basic of proving must be there. The basic of the proving thinking. Okay? Next, identity. I give you the answer, no identity. I want you to prove it on your own. Plus proof, proof on your own. Inverse also. Okay. For inverse, I can tell you the answer. There is no identity. Okay. How to answer if there is no identity? For inverse, no inverse for every element here. Because is the reason that you need to tell, is the proving themselves, because there exists no identity. Some of my students answer like this: as there is no identity, therefore there is no inverse. Also can. And let's proceed to the fifth one, because I want to check whether it's an abelian or not. Commutative. This one very simple counter example. It's not commutative simply because 2/3 is not macam ni lah. 2/3 is not equal with 3/2. Siap. Counter example again. My last conclusion is that, of course, division of integer is not abelian group. Let's look at the whole answer. Okay. I just managed to mention to you, and including the proof from your friends, is that division of integer is not even a semi-group, it's not a monoid, it's not a group, and it is also not an abelian group. This concludes this example. Any question before I proceed to the next important part? Here. Okay, no question, that's fine. Okay, we proceed with the next special group. Just now, we learned that this is the form of binary operation of G. Okay? And the previous example, I already showed to you the addition of integer. And the second one, the division of integer. Again, this G can change. The binary operation also can change. For this part, right now, I want to teach you the binary operation of Zn. Zn star, and also lastly Un. Then we finish the lecture. I just show you one example, this one, group. The other three I just mentioned what is Zn, Zn star, and Un. Okay? Then we will finish the lecture today. But not finish yet, sabar. We start first with the what is Zn. Zn, the element inside. Okay, I start with Z first. What is the element of integer? This one you can mention there are infinitely many integer. -3, -2, -1, 0, 1, 2, 3, blah blah blah.
is infinite. Zn is a finite set, not infinite, and it starts from 0, 1, 2, up until n minus 1. Therefore, the example for Z4, it contains this element 0, 1, 2, 3. But it's not stopped there. Z4 means this element. And then the binary operation, later I will say, later. We start with the fundamental first. See, Zn star means not including 0. That is only the difference between Zn. Still until n minus 1. Therefore, for Z4 star, it means from 1 to 3. For Un, okay, you can read the definition on the left. Un represents integer, let's say A. A positive integer which is greater than or equal to 1, yes, it's a positive integer, relatively prime with n until n minus 1. Okay, this one, you need to recall back the definition of relatively prime. It means that the element of a positive integer in the given un must be relatively prime with n. It means the GCD, greatest common divisor with the n, must be 1. Let me show you the example of U4. 1. Is it inside here? If it is inside U4, then it means the GCD between 1 and 4 is 1. And indeed, the GCD, greatest common divisor between 1 and 4 is 1. So the first element of U4 is 1. Now 2. 2 GCD between 2 and 4 is 2. Therefore, 2 will not be an element of U4. 3 is there up until 3 lah. Okay, so this is the element of U4. Let's look the example of U5 here on the left. 1 is relatively prime with 5. 2 is relatively prime with 5 because the GCD is 1. 3 also, GCD is 1. 4 and 5, the GCD is 1. And U8, 1, 3, 5, 7, all the integers inside this given U8 is relatively prime with 8. This is the fundamental. I recall back, Zn, 0 until n minus 1, Zn star, starting with 1, excluding 0 up until n minus 1. For Un, is a positive integer which is relatively prime up until n minus 1. Now we proceed with the actual question here of example 5.4. How to develop a Cayley table for Z4. This question is really not that complete. It must state like this. Prove Z4 under addition is a group or not, by checking all the properties of a group. It is established, you know already that Z4, 0, 1, 2, 3. But how to represent the binary operation is quite impossible if you don't have the Cayley table. Yeah. Okay. Zero, 1, 2, 3. Plus here. 0, 1, 2, 3. Okay, listen carefully. This is how we develop the element inside. For the first 0 and 0, 0 plus 0, you just add it, becomes 0. But that is not how it developed inside here. This 0 later will be mod with 4. Remember chapter 1, modular arithmetic. 0 mod 4 is 0. So the answer here is 0. 0 plus 1 is 1. 1 mod 4 is 1. And I proceed later, it becomes like this. Nothing special yet. And even some of you find out to develop this first row is confusing because how can 0 mod 4 is 0? Okay? You represent back as a division algorithm, you will see that. I want to show this. At this part, 1 plus 3 is 4. Okay? Later, 4 mod 4. 4 mod 4 dapat berapa sebagai remainder? Is 0. That's why chapter 1, recall back if you forget modular arithmetic. But for the timing, I will not teach you back. Abstract algebra is the master for, you must master from the first one up until now. This one will be 2, 3, 0. 2 plus 3 is 5. 5 mod 4 is 1. And lastly, 3, 0, 1, 2. This is how you get the Cayley table for addition. Let me do for you right now on a different topic, different Cayley table. Okay, I will still answer this question later. But for now, suppose I get this question. Develop Z4 under multiplication. Okay, again, the same principle, Z4 should consist 0, 1, 2, 3. This time multiply 0, 1, 2, 3. The thinking right now is multiply, then you mod 4. So 0 times 0 is 0, 0 mod 4 is 0, 0 times 1 is 0, 0 mod 4 and 0, and then you get like this. Okay? Next, this is 0. Start 1 times 1, 1. 1 mod 4. Don't forget mod 4 sebab ni masih 4 sana. 2, 3. Nothing special yet up until this point. 2 times 2. 4. 4 mod 4 is 0 here. 2 times 3 is 6. And as you know, 6 mod 4 is 2. This one becomes 0, 3, 2, 3 times 3, 9. 9 mod 4 is 1. Okay? This is how to develop for different operation. In my video rakaman, recording of the video, I state in the video is that it's hard to do for subtraction and division. There's a reason why. I can show it to you a little bit only. For example, tolak, subtraction. Why is quite impossible for you to do that? Okay, if you work from the left to right, 0 minus 0 is 0, 0 minus negative 1, 0 minus negative 2, negative 3. 1, 0, negative 1, negative 2. Some of my students will actually do this. They don't work from the left to the top. They do from the top to the left. 0 minus 0, 0. 1 minus 0, 1. 2 minus 0, 2. 3 over 0, 3. Negative 1, 0, 1, 2. You can take a look. You will produce actually two different Cayley table. I don't do for the remaining two. This happened because I don't say it's impossible. I say that it should have two answers, because subtraction is not commutative. That's why you will be a little bit confused at this point. Yang mana satu betul? Which one is correct? Both of them are correct at your own orientation. Because subtraction is not commutative, that's why it happens for both Cayley table. For multiplication, you work from the left to top, or the top to the left, you get the same answer. Trust me. And same goes for plus. Okay, now I will finish this question. Prove that this is a group. Listen carefully. Now I finish the Cayley table. Now I can answer whether it's a group or not. We start with the closed. Okay. For the closure, we take two elements from Z4, be it 0, 1, 2, 3. Is it closed? The answer must have Cayley table first, because my answer will refer to my Cayley table. Based on Cayley table, it is closed. And some of you might argue with me right now. Just now, addition of integer, I mentioned in the word of statement. Right now, why I just mentioned this? This is why, if you want to explain every possible combination of the two integers inside Z4, then it will be lengthy. This is what I meant. I take 0 plus 1 mod 4. What will be the answer? I take 0 here plus 1, you get 1. 1 mod 4 is 1. And then you say, yes, 1 is an element of Z4 also. Okay, you are true. Now, because I just mentioned 1, why not I mention 2 plus 3? 2 plus 3 mod 4 is 1. 1 is an element of Z4. How many possible combinations in there? There will be 16 possible combination. 4 times 4, yeah. 0, 0, 0, 1. Yes, yes, yes. Including the 1, 0. 0 plus 1 is not the same with 1 plus 0 for the in terms of representation, although the answer is with 1 as well. But again, you need to show me 16 of this thing, which is not appropriate, I might say. Therefore, it's sufficient actually for you to just use Cayley table. You already done that. Kejap. You already done that with the condition that your Cayley table is true. Based on Cayley table, it is closed because the thing inside here, that in the blue circle, all of them, 0, 1, 2, 3, 1, 2, 3, 0, semua kat dalam ni, is an element of Z4. So this is the answer that can already be accepted. You don't need to mention all 16. If it is a finite case, you must mention all, right? So you waste your time. We decide that with the condition of your Cayley table is correct, this is sufficient. Okay? For the next one, associative. Again, it's the same principle. There are many combinations that you must show. So it's enough based on the properties of integer. Just now I mentioned to you that the addition of integer is associative, right? The addition of integer modulo n is also associative. Right now, to put into the statement based on the properties of integer addition, This Z4 under addition is associative. We can accept this answer already because it's a well-known properties of integer addition is associative. So do Z4 under addition. Some of my students wants to write like this also can. I've seen this example. As Z plus is associative, Z4 plus also associative. I can also accept this answer. Okay. We proceed with the third one. Please be patient. Sikit lagi. Identity, which is very interesting because I want to know what is the identity. So you look based on the Cayley table here. You must know how to read it. What is the element? For example, if I take 0 there, 0 here, I guna mouse. 0 plus 0, mode 4, you get back itself, which is 0. 1 plus what identity, you get back 1. 2, you plus what element, you get back 2. And 3, you plus with what, you get back 3. And it's very easy to say that E equals to 0. You can check here. You 0 plus 0 dapat balik 0. 1 plus 0 you get back 1. 2 plus 0 you get back 2. 3 plus 0 you get back 3. The identity exists. The identity is 0. Very clear actually. And right now, if you have identity, you need to check for inverse. And for the inverse case, you need to tell me explicitly what is the inverse of 0, 1, 2, and also 3. You must mention each of it. Because this is a finite case, you must mention all. Let's do this kind of thinking. What is 0 binary operation, in this case plus mode 4, that's why I represent as 0. 0 inverse, you get 0 inverse, binary operation with 0, you get back the identity which is 0 itself. Banyak sangat 0. What is the 0 inverse? Is actually itself. For 1, it's different. 1 binary operation with 1 inverse, you get back 1 inverse, binary operation with 1, you get back 0. This one very clear. If you look at the Cayley table here, alamak. Okay. 1, you add up with what modulo 4, you get back 0. I repeat. 1, you add up with what element on the top here, you get back identity which is 0. It is 3. You dapat 0. Therefore, the inverse of 1 is 3. The inverse of 2, you get 0, is itself. And the inverse of 3 is 1. If you look this answer, it's quite interesting if you understand the chapter of chapter 2, function. The inverse of 1 is 3, the inverse of 3 is 1. If you put into the diagram, this is actually an injective function. This is actually a one-to-one function. It is related. Okay? I finished stating all the possible inverse. Now I can say conclusively is that actually this Z4 under addition plus modulo 4 is proven to be a group. Tada! Okay, finish. I add one more, by the way, about some of you might ask how to prove commutativity. Okay. if it's abelian or not. Commutative, again, the same principle like number 1 and number 2. There are many combinations. You must show that 0, 0 is equal to 0, 0, 0, 1 equal to 1, 0, 1, 1, 1, 2 equals to 2, 1, and so on. Banyak kombinasi. You can state based on properties of integer addition, because integer addition is commutative. Therefore, Z4 under addition is also commutative. Ni soalan tambahan, extra question. It means that not only Z4 under addition is a group, it is also an abelian group. Ada soalan? Oh, 3. 3. Apa 3? Oh, okay. Soalan tadi. Sorry Saya lambat sikit. I will be a little bit late when want to read the chat. Sorry That's okay. If you want to open the mic to answer my question, that's fine. I will feel more livelier. I will not feel like a crazy person talking alone in this room. Okay, let's sum up this example. What you learned today is very basic for this abstract algebra chapter. You must master every closed, associative, identity, inverse, and also commutative as applicable to any G and also applicable to any binary operation. If you have any question, I will let a time for 1 to 2 minutes for you to ask me a question. You can open the mic if you want to ask. Krik krik. Korang ni lah. I hope you understand. Seriously, I'm worried because I cannot see your face. I cannot see your body language to indicate. If it is a face-to-face class, saya cakap orang, okay, when I talk, I can see your eyebrow curled. I tahu you tak faham lah. I know that you don't understand. Okay, ada soalan. So far so good. Okay, Dia Rahman Daniel. Okay, that's fine. That's positive. That's positive. I'm glad that Dia understand. Bear in mind is that why I don't afraid to say that this kind of question will come out, because I always just change this part. I change G, I change binary operation. There are many possible questions that can be asked. Some of my students tend to memorize all possible combination. There exists a student from the previous semester try to memorize all possible answer. My suggestion for you, yes, you can do so. Memorize this answer, for example, for this kind of question. For example, if I ask this question in final exam, prove that 4 plus is a group. Some of you with a good memory can already answer it. But my advice for you is try to understand the definition better, then you can apply it to any kind of G and any kind of binary operation, inshallah. Okay, no question. And this is my request. Before I end the meeting, to avoid me to do the editing so much, I'm still learning, Filmora, sorry. I will try my best to do it as fast as possible. But for now, our lecture concludes here. Don't forget to sign out when I end the meeting. If no question for you guys, to me right now, I end this lecture with thank you. Assalamualaikum warahmatullahi wabarakatuh and goodbye. Sir, do you need to apply for license? Apa ni? License apa ni, Ong?
Sir, today got news, the parliament, the MCMC, the multimedia, they said what? any video recorder need to apply for license from FINAS?
Apa-apa video?
Oh,
Okay, I will check it back. Tapi kalau semua video, kalau video pengajaran kena minta license FINAS tu, saya tak undi ikut PN kot. Cannot lah. This is an academic purpose. But I will check your claim later. I will listen for any policy developed in the parliament today. Okay, thank you so much.
okay.
Alright, goodbye. Okay, log out please semua. Log out Okay, Assalamualaikum and goodbye again.